rod length and the crank pin radius. Finally, we use the equation from Hayward to calculate the volume for each crank angle. We use a for loop to accomplish this. Now let us take a look at the main program. Coding the main program is very simple. We define the geometric parameters and then supply them to the function that we have written. While writing functions which accept multiple inputs and return multiple outputs, you should remember that the order is very important. If you change the order, then you will be using the wrong values. Finally, I make a plot of the volume versus crank angle, and that's it. In the next part of this video, we will animate the piston motion and learn about automatic plot generation ratio. The objective here is to plot the in-cylinder volume as a function of crank angle, and this plot is referred to as the volume trace. I will be writing this program using functions. The function will take the geometric parameters as the input and provide the volume trace, the stroke volume, and the clearance volume as outputs. The coding part in this case is very simple. We first define an array to store the crank angle, after which we calculate some basic quantities which we are all familiar with. The stroke volume is basically the volume of a cylinder. The clearance volume is calculated from the stroke volume and the compression ratio. The crank pin radius is half of the stroke length. And finally, we define a constant R, which is the ratio of connecting rod length. As we all know, kinematics defines how a particular object moves without taking into account the forces acting on the body. In this video, we will look at the kinematics of the slider crank mechanism. This mechanism is used in several applications. One of them is the internal combustion engine. The piston in an engine moves according to this mechanism, and by describing the mechanism mathematically, we can determine useful quantities such as the volume trace, and this is exactly what we are going to do today. For a given set of geometric parameters, we are going to calculate the volume of the combustion chamber. The geometric parameters are the bore, the stroke, the connecting rod length, and the compression ratio. The objective here is to plot the
spark plugs. Now looking at an actual engine, here is the generator and the battery. Together at the rear of the engine are the coil, the distributor cap containing the contact swept by the rotor itself, and the points which sometimes need adjustments. And finally, in the cylinder heads, the spark plugs. The engine on this model chassis contains nearly all the parts found in a working engine. Let's break it down to its fundamentals and then build it up again. Here's the heart of the engine, the cylinders and pistons. This engine, known as a V8, has two banks of 4 cylinders each, driving a common crankshaft. The camshaft, geared to the crankshaft, lifts and lowers the valves in the cylinders. Now the right and left cylinder heads, containing the valves themselves and the valve lifters. The distributor at the rear of the engine is also driven from the camshaft. Now the fan, the generator, and a part of the cooling system. Here, flashing lights simulate the firing of the spark plugs as the rotor supplies current to each in proper firing order. Continuing the build-up, here are the carburetor and the manifold. And finally, the air cleaner atop the carburetor. Here is a rear view showing how the pistons drive the crankshaft. And down through the plastic housing, we can see the gearing connecting the camshaft to the distributor. 4, 6, and 8. Modern auto engines have a number of cylinders driving one crankshaft. Gasoline from the tank is pumped by the fuel pump to the engine's carburetor through the fuel lines. The carburetor mixes the gasoline with air to form the explosive mixture that drives the pistons. Here's a closer view of the carburetor. A linkage connects the accelerator pedal with a valve in the carburetor. Stepping on the gas opens this valve wider, increasing the gas flow and speeding up the engine. Easing off on the pedal reduces the flow and the engine slows down. Here on an actual engine are the counterparts of the fuel system just diagrammed. The fuel pump, the fuel line from pump to carburetor, and the carburetor itself with its air cleaner removed. Here is the linkage connecting the carburetor to the accelerator pedal. Modern auto engines have a number of cylinders driving one crankshaft. Gasoline from the tank is pumped by the fuel pump to the engine's carburetor through the fuel lines. The carburetor mixes the gasoline with air to form the explosive mixture that drives the pistons. Here's a closer view of the carburetor. A linkage connects the accelerator pedal with a valve in the carburetor. Stepping on the gas opens this valve wider, increasing the gas flow and speeding up the engine. Easing off on the pedal reduces the flow and the engine slows down. Here on an actual engine are the counterparts of the fuel system just diagrammed. The fuel pump, the fuel line from pump to carburetor, and the carburetor itself with its air cleaner removed. Here is the linkage connecting the carburetor to the accelerator pedal. The engine's electrical system supplies the spark that fires the fuel mixture. As the engine rotates, it drives a generator which keeps the car's battery charged. The battery supplies electricity to the coil, which boosts the current to a voltage high enough to produce a spark, and then sends it through the distributor to the spark plugs located in the cylinders. The distributor distributes electrical current to the proper spark plug at the proper time. Inside the distributor is a rotor, which as it turns touches a series of contacts, one of which is wired to each spark plug. The points open and close as the rotor turns, interrupting the current to produce the fuel-igniting spark. Here again are the major parts of the engine's electrical system: the generator, the battery, the booster coil, distributor,
Variable ignition timing advance. Modern electronic fuel injection systems often control more than just fuel delivery. The spark events are also controlled by the ECM. Depending upon engine speed and engine load, the spark event may be required to occur much sooner or later in relation to the piston traveling toward top dead center. Variable spark advance is a tool used to always keep the engine producing maximum leverage on the connecting rod and crankshaft, thus making the most torque and efficiency possible. If we take a closer look at the process, fuel takes some time to burn inside the combustion chamber relative to engine speed. To accommodate this, the spark event needs to happen much earlier than the piston achieving top dead center. Here we can see the fuel-air charge being compressed during the compression stroke. Once the crankshaft reaches a predetermined angle, as pointed out to the ECM by the crankshaft position sensor, the ECM closes the ground to the ignition coil, completing a circuit. Up to 15,000 volts now travel at the speed of light to the spark plug and jump across the air gap to start the fire in the combustion chamber. Four-stroke engines require 2 full turns of the crankshaft or 720 degrees of rotation to complete 1 full cycle for an individual cylinder. If we look at the spark events during various operation modes, we can see the difference of when the spark occurs relative to engine rotation degrees. Let's look at some varying operating condition examples. When the engine is operating under moderate load and high-speed conditions, the proper spark advance will be delivered at 340 degrees, or 20 degrees before top dead center. When the engine is operating under light load and high-speed conditions, the proper spark advance will be delivered at 319 degrees, or 41 degrees before top dead center. When the engine is operating under heavy load and high-speed conditions, the proper spark advance will be delivered at 349 degrees, or 11 degrees before top dead center. Here are examples of how improper timing can affect the engine's performance. Let's say the engine is operating under moderate load and high-speed conditions, and the spark advance is delivered too early at 319 degrees or 41 degrees before top dead center. This can cause improper combustion events like detonation that affect power and performance and can even damage the engine. As a final example, say the engine is operating under moderate load and high-speed conditions, and the spark advance is delivered too late at 355 degrees or 5 degrees before top dead center. This can cause poor engine power, excessive exhaust gas temperature, and a glowing exhaust system due to the wasted energy being placed into the exhaust instead of producing useful work. Once the mixture is ignited, it rapidly burns and expands. This expansion of gases is what is used to drive the piston down, thus turning the crankshaft. This process requires a careful balance, as there are many ambient variables that affect the optimal timing. This functionality is a major improvement over a fixed timing system, and is the other half of how EFI brings refinement, performance, and fuel economy improvement over their carbureted counterparts.
opening and closing. The first stroke is intake. The piston moves downwards, decreasing the pressure in the cylinder. The intake valve opens, and a mixture of air and fuel flows from the carburetor into the cylinder. The second stroke is compression. Both the intake and the exhaust valves are closed then. The momentum of the crankshaft and the counterweight causes the piston to move upwards, compressing the mixture of air and fuel, and thereby increasing its temperature. The third stroke is the power stroke. The spark plug ignites the compressed, heated mixture of fuel and air. The explosion pushes the piston down. The fourth stroke is the exhaust stroke. The piston moves upwards, the exhaust valve opens, and the exhaust gases are expelled.
Dizel yakıt sistemleri genel olarak yüksek basınç prensibiyle çalışır ve 3 temel unsurdan oluşur. Bunlardan ilki mazot pompası, ikincisi reel borusu, üçüncüsü ise enjektörlerdir. Depodan gelen mazot pompa vasıtasıyla basınçlandırılır. 2500 bar basınca ulaşan mazot reel borusu aracılığıyla enjektörlere aktarılır. Enjektörler mazotu atomize hale getirerek eşit ve düzenli bir şekilde piston bloğuna püskürtmekle görevlidir. Enjektörün dengesiz mazot püskürtmesi motorun tam verimli çalışmasını engeller. Bu da araçta çekiş düşüklüğü, duman atma gibi başlıca problemlere sebep olur. Enjektörlerinizin uzun ömürlü olmasının en önemli kuralı temiz ve kaliteli mazottur. Bizim tavsiyemiz mazotunuzu kaliteli bir markadan ve sürekli aynı istasyondan almanızdır. Ayrıca mazot filtrenizin her bakımda değişmesi enjektörleriniz için çok önemlidir.
Good? Yeah, we're good.
coolant temperature sensor is located near the thermostat housing. It will turn on the radiator fan if the coolant to the radiator side is at high temperature. Now, the hot coolant in the radiator will release its heat to the atmosphere with the help of the fan. At the same time, the cold coolant received from the radiator will start to absorb the heat from the engine for the next cycle. Heating liquid inside a closed system always builds up pressure. So, how to maintain the pressure? Here comes the role of the radiator pressure cap. It consists of a spring-loaded valve mechanism, which will respond to higher pressure. Reaching a pressure above 15 psi will push the pressure cap valve, and the coolant flows to the expansion tank, until the pressure goes down to operation level. And when the system cools down, the vacuum inside the system sucks the impeller. It is driven by the engine itself, using a serpentine belt. The serpentine belt also drives the power steering pump, alternator, AC compressor. But for now only water pump is shown. Now let's see the connections. The thermostat bypass hose. The thermostat housing. Inside the thermostat, the radiator, and the radiator fan. The lower radiator hose. The water pump outlet hose. The upper radiator hose. The coolant expansion tank. The expansion bleed hose. Coolant overflow hose. So, finally, let's get into the working, starting with the thermostat. These are the main parts involved in an engine cooling system. Now, let's see how these parts works together. The pistons are contained inside the engine block, in which each of them will function. Above the engine block comes the head gasket, which provides sealing between engine block and engine head. It avoids compression leaks, and oil or coolant leaks into the cylinders. Above that comes the engine head. The engine is having a safe passage, through which the coolant can flow without entering into the cylinder, or mixing up with the oil. This passage is known as water jacket. Let's put the parts one by one, and see how it works. The water pump pumps the coolant throughout the system with the help of the radial impeller. The thermostat is actually a valve, which regulates the flow of the coolant. It will always be covered in the coolant, so that the temperature can be sensed. Let's start the operation from a cold engine. When the engine is cold, the bypass valve stays open. So, the coolant bypasses the radiator and recirculates through the engine. This helps the engine to heat up to operating temperature quickly. Eventually, the coolant temperature increases by absorbing the heat from the engine. Once the coolant starts to reach higher temperature, which is usually between 160 to 190 Fahrenheit, the bypass valve will start to close, and the main valve will start to open. This allows the cold coolant from radiator flow to the engine side, and the hot coolant from engine side flow to the radiator. In most cars, the system sucks back the coolant from expansion tank. In case if there is too much pressure build-up in the system, due to trapped air, or other failures, the coolant in the expansion tank will be pushed out through the overflow hose. The car heater system is a part of the engine cooling system. The heater system comprises of the heater core, inlet and outlet hoses, a heater control valve which is optional and cannot be found in all vehicles. The heater core acts as a radiator, dissipating heat from the hot coolant to the vehicle interior, using a car engine is basically an internal combustion engine where power is generated through expansion of high temperature and high pressure gases. A lot of heat is generated due to the combustion gas and the friction of mechanical parts. For sustained operation, these excess heat should be removed from the engine and kept at operating temperature. Now let's see the parts involved in cooling the engine. The main parts for cooling the engine are water pump, radiator, thermostat, coolant temperature sensor, and coolant. First, the water pump. Water pump is the heart of the cooling system, which pumps the coolant. It consists of an impeller, a pulley flange, and an O-ring. The impeller is driven by the engine drive belt through a pulley. Next, the radiator. The radiator is a heat exchanger used to transfer the excess heat developed by engine to the atmosphere. The radiator is having an inlet port, outlet port, a drain plug, and a radiator pressure cap. The radiator pressure cap plays a vital role in the cooling system, which will be explained later. Next, the thermostat. The thermostat is a valve which regulates the flow of the coolant and helps to maintain the proper operating temperature for the engine. The thermostat consists of a frame, charge cylinder, main valve, main spring, bypass valve, and secondary spring. Next, the coolant temperature sensor. The coolant temperature sensor is used to monitor the engine temperature. The ECU will use this data to manage fuel injection and ignition time. Some engines have more than one coolant temperature sensor. The data is also used to control the radiator fan and to update the temperature gauge on the driver console. The coolant temperature sensor consists of a sensing probe and an electrical connector. Most coolant temperature sensors are negative temperature coefficient type, which means as the temperature increases, the resistance will decrease. The CTS can be a 2-pin type, or a 3-pin type, depending on the make of the vehicle. These are the main
due to inertia of the motorcycle rear wheel, and the outer basket spins due to engine power. This is why these two components start spinning at different speeds. In order to interlock with both of these non-synchronized spinning components, the hypothetical connector will have to spin at 2 different speeds at the same time, which is impossible. For example, if it matches the inner hub speed, then interlocking this connector with the outer basket will be either impossible or too difficult. To eliminate this problem, the clutch pack is used in place of this hypothetical connector. Unlike our hypothetical connector, the clutch pack is a combination of separate circular plates. Let's take any two adjacent plates from the clutch pack. One of them is a friction plate, and the other is a steel plate. The friction plate has teeth on the outer circumference, which always interlocks with the clutch basket and can slide sideways along this clutch basket. Now let's understand how a clutch works. The clutch basket freewheels with respect to the gearbox. The engine power will spin the clutch basket, but it will not transfer any power to the gearbox. However, the inner hub is connected to the input shaft of the gearbox. If we spin this inner hub, then it will also spin the gearbox input shaft. Let's take a hypothetical connector with teeth on its internal and external portion that can interlock with both the clutch basket and the inner hub. If we insert this hypothetical connector between the clutch basket and the inner hub, then we can spin both of these at once and the engine power reaches the gearbox. And if we remove this hypothetical connector, the clutch basket and inner hub will be independent again and the engine power is disconnected. But there is a problem in using this connector. When the connector is removed, the inner hub spins due to inertia of the motorcycle rear wheel. This will disconnect the inner hub with the clutch basket, and the engine power is disconnected. Several other plates are added to increase strength and surface area. Now let's understand how pressure on these plates are changed while riding a motorcycle. We use the pressure plate for this purpose. It has ducted attachments where a set of springs can fit in. A set of retainer bolts are screwed to the inner hub. This causes the spring to compress and apply force on the clutch pack, resulting in sufficient friction between the plates. We can release the pressure on the clutch pack by pushing the pressure plate outwards. We can control this pressure by pulling or releasing the clutch lever. As the clutch lever is pulled or released, a cable or hydraulic system rotates an actuator arm as shown in the clutch basket. The plate spins with the clutch basket but doesn't affect the inner hub. The steel plate has teeth in its inner portion, which always interlocks with the grooves in the inner hub and can slide sideways along this hub. This plate spins with the inner hub, but doesn't affect the outer basket. As these plates can slide sideways, we can press them together, gradually increasing friction so that both of them start acting like a single unit, like our hypothetical connector. With this arrangement, if we spin the outer basket, the inner hub will also spin. This will eventually transfer power from the engine to the gearbox. Even if the plates are spinning at different RPM at first, the gradual increase in friction between them will eventually synchronize them. If we release the pressure, the two plates become independent. This will disconnect the inner hub. Before going into the details on working of a clutch, let's see how it is assembled in motorcycles. The power from the engine is converted to rotary motion by the crankshaft as shown. This power is then transferred to clutch housing. The clutch assembly transfers power to the input shaft of the gearbox. The power is then transferred to the output shaft and eventually to the rear wheel of the motorcycle. The clutch assembly itself is a combination of several parts. It consists of a pressure plate held in place by using several springs and screws. This plate presses against the clutch pack. The clutch pack consists of several steel and friction plates placed in alternate positions. The clutch basket and the inner hub are assembled with their axes aligned to the input shaft of the gearbox. Now, rotates an actuator arm as shown in the animation. This arm presses against the push rod towards the clutch. This rod goes through a duct inside the input shaft and pushes the pressure plate, releasing the pressure on the clutch pack. When the clutch lever is released, the springs again apply pressure to the clutch pack as shown in the animation.
In diesel engines, the operating cycle starts with clean air being drawn into the cylinder, not a fuel-air mixture as in a conventional gasoline engine. The motion of the piston compresses the air, heating it to a high temperature. When the piston nears the top of the cylinder, fuel is injected under high pressure through a number of precisely machined holes in the tip of the fuel injector. The fuel enters the engine in the form of a fine spray, and the surface of each droplet quickly begins to vaporize on its path through the hot air. Spontaneous ignition takes place without the need for a spark, and rapid expansion of the combusting mixture increases the pressure in the cylinder, forcing the piston down and powering the vehicle. When the piston is close to its lowest position, the exhaust to its lowest position, the exhaust valve starts to open, and the exhaust stroke then drives the spent gases out of the combustion chamber, and the cycle starts again. In conventional gasoline engines, a mixture of fuel and air is drawn into the cylinder, compressed by the motion of the piston and ignited by a spark as the piston nears the top of the cylinder. The resulting combustion generates pressure which forces the piston down to power the vehicle.
Бам! Класс! Класс! Вот так вот. Класс! Все, не переходи, меняйся сторона. Меняйся, Жека. Смотрите, сейчас будет остывать и сразу менять цвет. Видите, белое типа матовое. Фух, вот пошла жара. Меняется, видите? Все, пушка. Держим. Это потрескивает. Вот сейчас видно будет тут хорошо. Знаете, типа как в вине. Сейчас, когда начнет остывать, сразу будет вот пошла жара. Оба-на. Опа, 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 опа. Все, сняли. Все, 3 литра турбо загрязовано. Теперь резервнуть, хон, пасок. И отдаем Максу, будет собирать.
Compressor wheel draws in air and compresses it. Then, the air passes through the outlet port and supplies the engine with oxygen. Let's have a look at the turbo and other components to have a better idea of the principle at work. The exhaust gas enters the turbine through the inlet port, drives the turbine wheel, and exits the turbine through the outlet port. Hereby, the compressor wheel draws in air, compresses the air and pushes it to the engine. Engines that have a turbo are known as turbocharged engines. A turbo only works efficiently if other components are part of the entire system. We need, for example, an intercooler because the air heats up when it's compressed. So the intercooler will cool down the hot air coming from the compressor, ensuring that more oxygen reaches the engine. The turbocharger comes into play. A standard turbo, as it is used in boats, airplanes and cars, is composed of a shaft with a turbine wheel on one end and a compressor wheel on the other end. The turbine wheel and the compressor wheel may look the same and are covered by a housing. The exhaust gas produced by the engine enters the turbine housing through the inlet port. At that point, thermal energy is converted into kinetic energy because of the constriction in the turbine. Consequently, the turbine is driven by kinetic energy. As the turbine wheel and the compressor wheel share the same shaft, the compressor wheel spins at the same speed as the turbine wheel. Consequently, the compressor wheel draws in air, and Albert Büchi, an engineer from Switzerland, is seen as the inventor of the turbocharger. At the time of its invention, and today, the turbo's purpose is to take advantage of the exhaust gas produced by the engine. Today, small airplanes and light aircraft are equipped with a turbo to remedy the problem of low air pressure in higher altitudes. Ships and boats also use turbocharged engines, just like most diesel engines of cars do. In a standard 4-stroke diesel engine, air is forced into the cylinder by atmospheric pressure. This is the reason why this kind of engine is known as a naturally aspirated engine. At times of high RPM, for example on the highway, the atmospheric pressure will not push enough air into the cylinder. Consequently, the engine cannot run efficiently. Here's the engine. That makes the engine much more efficient. Furthermore, a valve, which is also known as a wastegate, is used to divert exhaust gas away from the turbine when too much exhaust gas is produced by the engine. So it limits the rotational speed of the turbine wheel and consequently the compressor wheel so that the turbocharger won't be damaged.
And we're just going to fill it back up with oil. So you fill it back up at the top through the oil filler neck. The oil then drains down into the bottom of the engine, into what's called the sump. Now when we start the engine, the rotational movement of the crankshaft, etc., will start to turn the oil pump, which draws oil up from the sump and then into oil filter to filter out the oil. It then goes up to the oil cooler. So the cooler is there to cool the oil down once the engine gets hot. The oil then is passed on through some channels through to the main end bearings and the big end bearings of the crankshaft and the conrods. The oil is then passed up to the top of the engine, up into the cylinder head, where it then lubricates the valve train and the camshafts. So all of this takes around about 12 seconds from a dry engine, so you can